You've heard this before. More stars in the observable universe than grains of sand on all of Earth's beaches. You heard it, you nodded, you thought, that's a lot, and you moved on. I know, because I would have done the same thing. But you didn't feel it, not really. And there's a difference between knowing a number and actually sitting with what it means. Because this isn't a fun fact to drop at dinner. It's a measurement, a hard, careful, scientifically derived estimate. And when you follow what it actually implies, not just the count, but what each of those objects is, what surrounds them, how we know, and what we still don't, the universe stops being backdrop and becomes something almost unbearably strange. So let's do this properly. Let's feel the number. And then let's follow it to where it actually leads. Start with what we're counting, because star sounds familiar, and familiarity is the enemy of understanding here. A star is a gravitationally bound nuclear fusion reactor, a sphere of plasma, matter so hot that atoms can't hold together, electrons stripped free, nuclei moving fast enough to collide and fuse. Gravity pulls the mass inward. The energy released by fusion pushes outward. The star is the balance between those two forces, sustained across millions to billions of years. Our Sun, 1.4 million kilometers across. You could fit over 1 million Earths inside it. Its core temperature is 15 million degrees Celsius. Every second, it converts 600 million tons of hydrogen into helium, and the mass difference, that tiny fraction that doesn't add up, is released as energy. That energy is what lights our days, drives our weather, powers every living thing on Earth. And the Sun is average. Genuinely, statistically average. A G-type main sequence star, one of the most common varieties in our galaxy, unremarkable in almost every measurable property. When astronomers want a reference point, they use the Sun because it's typical, not because it's special. Stars range from red dwarfs, dim, cool, barely above the minimum mass needed to sustain fusion, burning so slowly they'll last trillions of years, to blue supergiants, hundreds of times the Sun's mass, so hot their surfaces blaze at 40,000 degrees Celsius, burning through their fuel so recklessly they die in a few million years and explode. Between those extremes, every size, every temperature, every color, every lifetime. The number we're about to deal with is not a count of distant lights in the dark. It's a count of nuclear reactors, each one a sun, each one potentially a center of a solar system, scattered across space in numbers that require a different kind of arithmetic than we normally use. So how do we count what we can never count individually? The method is estimation, but careful estimation, the kind that can be checked, challenged, revised, the kind that scientists have spent decades refining. Step 1. Count the galaxies. The Hubble Space Telescope once pointed at a patch of sky, a patch covering 1/13 millionth of the total sky, an area smaller than a grain of sand held at arm's length, and took a very long exposure. In that tiny sliver of apparent darkness, approximately 10,000 galaxies, entire cities of stars, each one so far away it looked like a faint smudge. Scale that up to the full sky, roughly 2 trillion galaxies in the observable universe. That number, 2 times 10 to the 12th power, was revised upward tenfold from earlier estimates published in 2016, when deeper analysis suggested we'd been missing most of the smaller, fainter galaxies in our counts. Step 2. Estimate stars per galaxy. The Milky Way contains somewhere between 200 and 400 billion stars. Some dwarf galaxies have a few billion. Some giant elliptical galaxies contain several trillion. The average, accounting for the full distribution, is uncertain, but a conservative working estimate is around 100 billion stars per galaxy. Multiply 2 times 10 to the 12th power galaxies times 10 to the 11th power stars per galaxy. That gives roughly 2 times 10 to the 23rd power stars, 200 sextillion. Written out, 200 quadrillion. Now the sand. Researchers at the University of Hawaii estimated the number of grains of sand on Earth's beaches, accounting for the width and depth of beaches worldwide, average grain size. Their answer? Approximately 7.5 times 10 to the 18th power, about 7.5 quintillion grains. The stars win, by a factor of roughly 10,000 to 1. There are not just more stars than grains of sand, there are vastly more, enormously more. For every grain of sand on every beach on Earth, there are something like 10,000 stars. And this is only the observable universe, the sphere of space from which light has had time to reach us in 13.8 billion years. What exists beyond that boundary, we don't know. Possibly infinite space, possibly infinite stars. The count of 2 times 10 to the 23rd power might be a vanishingly small fraction of what actually exists. But let's stay inside what we can see, because even that is more than enough to work with. A galaxy. You picture a glowing spiral, beautiful, structured, the kind of image from astronomy photographs. That picture needs to be replaced with something that actually conveys the scale. The Milky Way is 100,000 light-years across. The Sun sits about 26,000 light-years from the center, out in the suburbs, in a relatively quiet spiral arm. Light from the galactic center, traveling at 300,000 kilometers per second, the fastest anything in the universe can move, takes 26,000 years to reach us. The light arriving at your eyes from the center of our own galaxy left before human civilization existed, before agriculture, before writing. Crossing the Milky Way at the speed of light takes 100,000 years. At the speed of Voyager 1, the fastest object we've ever launched into space, crossing our galaxy would take 1.7 billion years. Not from one galaxy to another, just across our own. The nearest large galaxy, Andromeda, 2.5 million light-years away. The light reaching your eyes from Andromeda tonight left when the universe contained no member of the genus Homo, before our ancestors were our ancestors. There are 2 trillion galaxies like this, each one a city of hundreds of billions of stars, each city separated from the next by distances that make the city itself feel small. Now here's where the number gets genuinely uncomfortable. We know, from the Kepler Space Telescope and its successors, that planets aren't the exception, they're the rule. Virtually every star we've examined carefully has planets. Some have one, many have several, some have more. The current best estimate is that there are more planets than stars in the Milky Way. The average works out to more than 1 planet per star when you account for multi-planet systems. If that ratio holds across the observable universe, and there's no strong reason to think our galaxy is special, then we're looking at something like 10 to the 24th power planets, a septillion planets, maybe more. Rocky planets in the zone where liquid water could exist on the surface. Estimates suggest hundreds of billions in our galaxy alone, hundreds of billions of potentially habitable worlds, in one galaxy, of 2 trillion, and the universe is 13.8 billion years old. Life on Earth took roughly 4 billion years to produce something capable of asking these questions. There has been time, on older planets around older stars, for that process to have occurred and completed billions of years before Earth even formed. With those numbers, the silence from the cosmos is the thing that demands explanation. Not the presence of life elsewhere, the silence. The Fermi paradox, where is everyone, doesn't get easier when you sit with these numbers honestly. It gets harder. Much harder. Now, here's something that changes the way the night sky looks once you really let it in. Every star you can see with the naked eye from Earth is in the Milky Way, our own galaxy. The farthest naked eye stars are a few thousand light years away. When you look at the night sky on a clear night, you're seeing your immediate stellar neighborhood, an infinitesimal fraction of one galaxy out of 2 trillion. And none of what you're seeing is current. The star 1,000 light years away, the light reaching your eyes left before the Norman conquest of England, before Genghis Khan, before the printing press. You're not seeing where the star is, you're seeing where it was 1,000 years ago, at the moment that light departed. The most distant objects we can observe, galaxies at the edge of the observable universe, their light left 13 billion years ago. We're seeing infant galaxies, some of which have since merged with others, evolved beyond recognition, or produced supernovae that scattered their material across intergalactic space. They may look nothing like what we observe. They may not exist in that form anymore. The observable universe is not a photograph of what exists right now. It's a layered fossil record, different distances showing different cosmic ages, all arriving at your eyes simultaneously, creating an illusion of a single present moment that doesn't actually exist. The concept of now across cosmic distances doesn't map onto our intuition of it. When you look at the night sky, you're looking at time, many different times, all at once. Let me tell you something about the stars themselves that the number obscures. The Sun feels like the prototype, the standard star. It isn't. Red dwarfs, small, cool, dim stars, make up roughly 70 to 75% of all stars in the Milky Way. They burn so slowly they last trillions of years. The universe is only 13.8 billion years old. No red dwarf has ever died of old age. Every red dwarf that has ever formed still exists, still burning, somewhere in the galaxy. Proxima Centauri, our nearest stellar neighbor, just 4.24 light-years away, is a red dwarf. It is completely invisible to the naked eye from Earth. The most common type of star in the galaxy, and the closest one to us, cannot be seen without a telescope. Sun-like stars, G-type stars like our Sun, make up only about 7% of all stars. We are not the typical product of the typical star. We are the product of a minority star type. The massive blue stars, spectacular, brilliant, violent, are rare and short-lived. They exhaust their fuel in millions of years and die in supernovae explosions. But those explosions matter enormously. Inside a star, nuclear fusion builds elements: hydrogen into helium, helium into carbon, carbon into oxygen, working up the periodic table toward iron. Beyond iron, fusion requires energy rather than releasing it. The star collapses. The supernova explosion produces the heavy elements, the gold, the uranium, the iodine, the zinc, and blasts them into interstellar space. That material drifts as gas and dust. Gravity gathers it into new gas clouds. New stars form, new planets, new chemistry. The carbon in your body was forged in a stellar core. The oxygen you're breathing was produced in nuclear burning and ejected in a stellar wind or explosion. The iron in your blood was made in a supernova. You are, in the most literal physical sense, made of material processed through stars that no longer exist. You are stellar debris that has temporarily arranged itself into something capable of wondering about stars. Now let me take the ceiling off. Everything I've described, the 2 times 10 to the 23rd power stars, the 2 trillion galaxies, the 10 to the 24th power planets, that's the observable universe, the sphere defined by how far light has traveled since the Big Bang. It's a horizon created by the finite age of the universe and the finite speed of light. It is not the edge of what exists. Beyond our observational horizon, space continues. The universe doesn't end where our vision does. Current cosmological models, the ones consistent with the flatness of space we measure, with the patterns of the cosmic microwave background, with the physics of inflation, are consistent with a universe enormously larger than the observable portion, possibly infinitely large. If the universe is infinite, genuinely spatially infinite, then the number of stars is not 2 times 10 to the 23rd power, it's infinite. Every configuration of matter permitted by physical law occurs not just once, but infinitely many times across infinite space. The observable universe is the part we can measure. It is not a description of what is. And that gap between the measurable and the real is one of the most honest and unsettling things in all of modern cosmology. We know what we can see, we don't know what there is. And even for the objects we can see and count, honesty requires admitting we don't fully understand the one closest to us. The sun still surprises us. For decades, the detected neutrino flux from the sun was wrong, only 1/3 the theoretical prediction. The resolution turned out to require neutrinos to have mass and oscillate between types, something the Standard Model didn't originally predict. Our nearest star taught us something fundamental about particle physics. The sun's 11-year activity cycle, the rise and fall of sunspot numbers, the periodic bursts of solar flares and coronal mass ejections, is still not completely explained from first principles. The detailed dynamics of stellar magnetic fields remain an active and incompletely solved problem. We have estimated 2 times 10 to the 23rd power stars. We do not fully understand the one that lights our days. Pick up a handful of sand. Seriously, imagine it. Every grain in your hand represents 10,000 stars. Not 10,000 lights in the sky, 10,000 nuclear reactors, each potentially with planets, each planet potentially with chemistry, each grain in your hand, 10,000 suns. Now multiply that handful by every beach you've ever seen, by every beach on every continent, by the sea floor, by every desert, every grain, 10,000 more suns, and the stars still outnumber them by 10,000 to 1. Every second of every day, somewhere in the galaxy, a gas cloud is collapsing under its own gravity and igniting, a new star being born. Somewhere else, a massive star is exhausting its fuel and beginning its collapse toward a supernova that will scatter its elements across light years of space. The universe is not static. It is not a finished object. It is churning, building, destroying, rebuilding, on timescales that make the entirety of human history invisible. You are a temporary arrangement of atoms forged in stars that died before the sun formed, on a planet orbiting an average star, in the outer arm of an unremarkable galaxy, in a cosmos containing 2 trillion more galaxies, and that's just what we can see. The rest is beyond our horizon. Not non-existent, just unreachable. The number of stars is not the point. The number is a doorway, and through it, the question that the number makes unavoidable. With 10 to the 23rd power stars, with hundreds of billions of potentially habitable planets in our galaxy alone, with 13.8 billion years of cosmic time, is the silence we've heard from the cosmos so far emptiness or just distance? Is the universe full of life we haven't reached, or is our wondering, this capacity to count stars, to feel the scale, to ask the question, the rarest thing in all of it? We counted the stars, we counted the sand. The stars won, decisively. And that's when the real question began.